So we will define one very important concept that you should understand and always remember, which is an interrupt. And we always say that the kernel of the operating system is interrupt driven. Everything on an operating system communicates using interrupts, both the hardware and the software. So I will give an example of a hardware interrupt in the next slide, but for software interrupts are actually things that you already know from software engineering and code development. So when we talk about things like exceptions, when you divide by a zero, things like system calls, which we will talk about later, but when you have things like infinite loops, for example, so these generate software exceptions to the kernel, and the kernel handles it. Now for hardware interrupt examples, think of a simple operation of writing or reading from an I/O device. When we say an I/O device, think of your hard disk, for example, right? Your HDD, hard drive disk. So simply writing data to the hard drive disk actually involves and takes so many interrupts. So for example, we have a user program, a word editor, for example, is currently executing on the CPU, and it needs data from the I/O device, right? So what happens is the CPU will send a request, an I/O request to the device, and then the device will start transferring the data that you need, and then transferring data will take some time because devices are usually slower than the CPU. So what will happen is that we will let the device do its own work, and then when it's done, the device will send an interrupt, right, to the CPU saying that I'm done copying the data and the data is now ready. So think of the interrupt as a signal or a notification to the CPU that there is an event happening and it has to be handled. And in this scenario, the event that had happened is the data transfer is complete, right? That the transfer is done. So once the CPU receives the signal, or what's called an interrupt, the CPU handles it and continues the execution of the program now that the data is available. Now, this is another important term and concept about operating systems that you have to remember, and it is the concept of multi-programming. To better remember this term, you can simply break it down into two parts: multi-programming, and it's simply the ability of having the ability of executing and running multiple programs on the system at a time. So we as users, we want to be able to interact and use multiple applications at the same time on the system. So multi-programming is what enables the operating system to do that, to manage multiple jobs at a time. And so the goal of the operating system is to always keep the CPU and the devices busy at all time, because these are very precious resources that the OS manages, and it doesn't want to waste its cycle, so it would schedule and manage and organize the different tasks and jobs on the system so that these resources have always a job to execute. And so now that we know what multi-programming is, then the degree of multi-programming is simply the number of tasks or programs that we have running at the system at a given time. Another very important concept of operating systems is the concept of time sharing, or also called multitasking. So the idea here with time sharing is having one single CPU and multiple tasks and jobs to be executed. The CPU is switching between different tasks or jobs, or what we will call later processes, very fast, which gives the illusion to the user that these tasks are executed in parallel. So we're trying to achieve parallel execution instead of sequential execution by rapidly switching between the different jobs or tasks that the CPU has to execute. So this figure compares the concept of sequential execution versus multi-programming, which we talked about before, and time sharing. So with sequential execution having two tasks to execute A and B, and we know that processes or tasks have actually two cycles. They need to do some computation on the CPU, right? So the CPU cycle, and they need access to data from I/O devices or input-output devices, which what we call input-output cycle. And so having two processes to execute with sequential execution, what we do is we start by process A, and then we wait for it to be fully completed, then we switch to process B. That's sequential execution. So you can see that process A starts here with CPU execution, and then at some point it has to switch to an I/O cycle right here. In the meantime, you can see here that we are wasting CPU cycles here where the CPU is idle and doesn't have another task to execute. Of course, assuming that on the system we only have A and B, and since we do have sequential execution, the CPU has to wait for A to fully finish execution. Then we switch to process B. So here you can see that we are wasting some CPU cycles, which the operating system tries to avoid. Now with multi-programming, so we do start a CPU cycle, right? And then when A has to switch to an I/O operation, instead of leaving the CPU idle, we do allow process B to start its CPU cycle, right? And then when A is done its I/O execution, it goes back to the CPU again, and so on, right? Now, after that, the time sharing started to emerge. So the idea there is we still have A and B, right, in this system, and you can see that the CPU here is trying to switch between A and B so frequently and so rapidly that we are actually given the illusion that A and B are actually executing in parallel. So the user gets that user experience and gets to interact with the two tasks at the same time. But we only have one CPU, right? One single processing unit, right? So they're not really executing in parallel. It's just that the switching between the two tasks is really fast. So we execute A for like 2 nanoseconds, and then we switch to B for 2 nanoseconds, and then we switch back to A, and so on. So that's the concept of time sharing or multitasking.